Buy them, but it's missing. Drop it somewhere. I'm not going to do it. I don't know that one in the possible places which I made. That's what I was thinking. Somewhere I'm going to drop.
Hello, hello. Hello, hello, hello. Hello.
Waiting for Raj. To ask. Can we switch this light off? It's 4 a.m. in Michigan. So next week it'll be evening. We'll be talking at 4.
Yeah, 4 or 2, right?
4 to
Then you'll be having classes from 7:30.
No, he's not teaching this semester.
But he's having some project.
Oh, yeah.
Take time for visiting somewhere.
Right? And hear you. What's the question?
How do you manage your sleep cycle?
For me, I mean, jet lag and all that. But I've been now, I came a week before the classes started. Yeah.
Oh.
So I had ample time. But from the next part two of that will be taught from Michigan. Right now, the time is 4 a.m. So he will be talking from 4 o'clock to 5:30 in the morning. And the other class, the 10:30 here is midnight there. Yeah, he just couldn't travel because there's a lot of, he's got a lot of project review meetings. He's got to travel to DC and all that. Yeah, otherwise sometimes we go from Michigan to say California for a conference or some other project meeting. It's 3 hours, but the 3 hours means, well, when you go from east to west, it's okay. Even as 8 o'clock meeting will be 11 o'clock for me, very comfortable. But when you come from California to Michigan, and if you have an 8 o'clock meeting, it's 5 a.m. for them, their time. You just go ahead and do it. So. So we're waiting for Neeraj.
I was inquiring for that key.
Did you get it? Okay, should we just get started then? Okay, so we will get started with the session 8, I think, and we're going to talk about microwave NDE. So in the morning, we talked about far field imaging. We're not going to say a whole lot about near field because there is no additional research that needs to be done for near field. So far field imaging, we saw the time reversal imaging methods. And one of the problems, there's a lot of advantages in doing far field, but the main disadvantage is diffraction limited resolution. So in this part, basically our motivation has been NDE of composite, metal composite joints and so on, like the morning. So basically here, what we'll talk about is more like a research topic. Again, it's all work under progress. We can see how we can enhance resolution of far field imaging using metamaterial lens. And we look at, we also have done some experimental implementation. We'll do all the simulation studies, results of simulation to show the feasibility, and then experimental implementation, which shows how we can do near sub-wavelength imaging. Okay, so this is an old slide. We have already seen this before. This is the motivation. You have composites are becoming very increasingly important. You can see here the aircraft. There are aircrafts made of composites, wind turbines, boats, and some wheels, all made of composite. And they have a lot of type of defects, very specific type of defect like fiber breakage and delamination and disbond and those kind of things, bond failure. So we want to detect those, and microwave is a very attractive technique for doing that. But again, this is the imaging, this other GFRP signal, far field image. The problem is one of imaging. Oh, I need to get this. One of the smallest defects, sub-wavelength defects cannot be imaged. Near field you can, but the standoff distance is small and time is large. Okay, so imaging resolution, we know that in conventional resolution, we can increase the resolution by simply using a conventional lens. But if you look at, I think this is what I referred to in the morning, if you look at the scattered field or the wave field and its Fourier expansion, the propagative spectrum, okay, when you look at the e to the j, this term, it will propagate only if this quantity is less than omega squared plus c squared, because, okay, let me see that. K squared and kg squared is propagating in the z direction. And when the frequencies are greater than that, then we have the evanescent wave, because you substitute it in your solution for negative values. For this will result in negative values, so there's another j coming out. So j squared gives you a negative, so exponentially decay. When it's positive, you have propagating waves. And this is the reason why you have this diffraction limit. Because if you look at this condition, this results in, if you apply all those, the values of these parameters, then you see that you come up with this thing, and so the resolution is given by lambda by 2 for maximum. Okay, and so in the case of ND of composites, one of the things we're trying to see is, can we get rapid inspection advantage in the far field and also enhance the resolution? And the solution for this question is metamaterials. Okay, yeah. So very briefly, very simply, metamaterials are engineered materials that can be prepared, that can be made to have certain properties that are not existing in naturally occurring materials. For example, they are all periodic structures, and the structural dimensions are such that the whole, when you have this periodic structure, the whole structure behaves like a homogeneous medium with properties that are not normally seen. For example, if you make a material with, you can make materials with negative refractive index. The conventional material, you have refractive index n is given by this, and epsilon and mu are normally positive quantities. But you can, and these are called as right-handed materials. And for such materials, you would have the top figure. You have light ray, for example, it will refract, but it will be in this direction. But you can design metamaterials where epsilon and mu are both negative. And in this case, you will have the light bending in a different direction that normally doesn't happen. So way back when metamaterials were first introduced, one of the commonly used method for building metamaterials was what this is called. This is this split ring resonator, and this simply strips. You know, we all know gratings, Bragg gratings also are like metamaterials. You have straight lines and then they refract in different ways. Okay, you can control the properties. Oh, what happened this way? I get it all out here. So these are called, you can control the dimensions. There are several dimensions here, which is the diameter of the split ring, the gap between the two rings over here, and then this gap and this gap. These are all the parameters. By controlling these parameters, you can control the frequency response of that this engineered material, and a certain frequency bandwidth, it will have negative refractive index. That's what we have seen. Okay, this is, again, these are all not my contribution. It was all something that we borrowed. People have already worked on it, and we tried to adapt it to our current application. That's what we did. So they show that SRR array has a negative mu when this omega is less than the plasma frequency, because this behaves like a magnetic plasma and with this kind of a response. Okay. So when this omega is less than this quantity in the numerator, this becomes greater, this quantity is greater than 1 and it becomes negative. So similarly, if I have an array of thin wires, this behaves like a negative epsilon medium. Again, mathematically, they've shown that this behaves like an electric plasma with this frequency response, and a certain frequency, the epsilon becomes negative. So we can further, so you can build these things with such that they have the same, they have negative epsilon, negative mu at a certain common frequency range. And there you have a negative index metamaterial. So these things, we simulated these, and basically we have these two frequency response, and we can plot those as a function of frequency for index of refraction, for epsilon, and show that there are certain frequency range where it becomes less than 0. Okay. So we've shown that for a certain dimensions of those split ring resonators and all that, you have plasma frequency, which is 20 gigahertz. For the second set of medium, you have this. And so combining the two, you can get, so basically we have a stacks of these SRR and these thin wires, okay? And we can build these two together. We can have a three-dimensional structure that will give us negative index. Now, going back again, so how does this help us? Okay. So, okay, this is a repetition of the thing, the normal lens. So if you have basically a metamaterial lens, if you model it by a homogeneous material with mu equal to -1, epsilon equal to -1, and so this one, we plot the fields, we see that the evanescent fields, which are for evanescent waves, are for these frequencies, it start increasing, it start rising in the negative refractive index. So you go back to that wave equation solution over there. If I put in a negative index, you'll get, instead of getting an exponentially decaying behavior like most evanescent waves, you get an exponentially increasing. And this, though, as I mentioned, the evanescent waves correspond to very small, large frequencies, high frequency content. High frequency content is high resolution. And this is under conventional imaging that is completely lost. With the metamaterial lens, you can actually get some of the information contained in the evanescent wave, and therefore this is called the super lens property of metamaterial lens. Okay, so again, these are all, I can give you references. These are none of these things are work that we did. Okay. Yes, Henry. Yeah. Those are the papers. So I think many of you even know about this. So how does, what happens when you pass a beam through a negative -1 refractive index. So if you apply Snell's law and you look at, say, this is an object, and you have a light beam coming from here, when this is negative, n is negative, it will refract in this direction, okay? And it will come to focus inside, and then it will keep going, and again here, from -1 to 1, it will refract in a different direction, and it will produce an exact image over here, okay? So it's that's how the focusing happens. And the evanescent waves, normally they decay completely, but once the evanescent waves start increasing exponentially, so you also get at the same point some focusing due to the evanescent wave. So, and this contains the high frequency information in the signal. And again, applying Lenz's law, you can see that this distance d1 plus this distance d2 equals to the total thickness of your metamaterial lens. Okay. So here, I think this is again a video, and you can see this happening. Oh, yeah. So let me play this video here. So this is the source in air. This is your homogeneous medium with negative refractive, negative mu, negative epsilon, -1, whatever. And we'll see what happens. If you just simulate the propagation. So at this point, it starts now focusing towards, converging towards that point because of the, refracting in the opposite direction. And then again, it starts diverging and converge up to this boundary. And at this boundary again, it starts converging. And so you get the behavior that we saw here. So you have, it starts from here, it goes, comes to focus inside, and then again, they go back and comes to focus outside. So that's one thing. So this just shows that. Okay, let me go back. I don't think. So this is what we call the perfect focusing property of the lens. So the condition, we have d1 plus d2 is t, n2 is -1, and the source is, this is the source that we applied. In all this is simulation. We haven't so far built a metamaterial, and we are just, the simulation is just a homogeneous model. It's modeling it is very simple. We are not modeling the individual unit cell in this. And we saw by simulation that D1 was 3.5 lambda 0, and D2 is 4.4, and D1 plus D2 is 7.9 lambda 0, and in practice, this was 8 lambda 0. So that's the error, for the simulation. Yeah, you have to select a frequency in that small narrow bandwidth where the index is negative. That's how you choose it. So you look at it for the whole frequency, and yeah, that's. Yep. But so if you know which frequency you're working with, you can design your metamaterial lens for that frequency, right?
That shape has to be comparable to wavelength.
Yeah.
For which that source is emitting particular EM wave. So initially that resolution was not that very nice. That means the size was too small to be detected by the person.
Yep.
Now we have metamaterial lens at high frequency.
Right. No, see, okay. I think I know where you're coming from. Forget about the initial part. We're now only looking at, can metamaterial increase the frequency? Okay. And what I want to show now is, if I know, if I for any design of a lens, it is effective only in a certain frequency band. So if everything is done in that particular frequency band, it will enhance resolution. So if that is proved, then you can go back and see what is it that you want to image, what is the frequency at which you are working with, where lambda is larger than the size. And for that frequency, I will design a metamaterial lens, which will and show that even with that frequency, with a large lambda, I can design a lens that will enhance the thing. Now,
complementary problem, when we change the lens, normal lens, optical lens, we try to zoom and see the same image.
yeah,
With the lens, we try to adjust the focal point and
right, yeah,
larger image.
right.
That's the same problem.
I see, because if you look at this per second image that just came here, okay, this is basically different distance. That's exactly what we are doing here. And all we are showing is that that ray diagram that I drew, that is valid, okay. So here D1 is 2.5 lambda, here it was 3.5, and D2 is 5.4 lambda here, okay. So the thickness is the same, but where it comes to focus is going to be different based on this distance. The D1 and D2 are going to be different. You can have different combinations of D1 and D2 that's equal to T. Okay, so far it's just a feasibility study. Okay, so I'll show that indeed, because if I put my sample right where this okay, let me do this. So what this means is that if I put my sample right here with the second focus outside the lens, my spot size is going to be small and I'll get better imaging. Okay, does that make sense? And simulation wise, we have shown that. Then we went back to do the experimental validation and showed that. So simulation shows, yes, it's feasible. All this is thing. Yeah, these are not. So how can I do the focusing property of the lens? How can I use it in composite inspection? So when you have nearly a plane wave impinging on the composite, there is diffraction limited resolution, okay? When there is no lens, this is what happens. This is how the field pattern looks like. It simply diverges from the source, okay? Now, when you have a lens over here, the field pattern is completely changed. It's over here, it's a, circular, but then this changes and comes to focus here, and then it diverges again and comes back to focus over here. So focused wave, then there is evanescent field that also comes. So at this point, I'm also getting some imaging from the evanescent field, and that is the secret why the resolution increases. Because we are getting resolution, increased resolution means what? Smaller object means higher frequency content. Okay, so if you just look at the source focusing,
Not thinking in that way. We never imagined that the solution was right in front of us in optical region, but
yes,
in the
right,
this happy
Yep.
region,
yeah.
megahertz or gigahertz.
Okay, so I think these two should be. Yeah, localized wave energy. So this is the focus energy in free space, basically. And this is the focusing with the lens. It looks like in the cross range, it is well localized. In the down range, this is not so well localized. Okay, so this is without lens. Oh, okay, so I'm sorry. This is, both of these are with lens. This is no in free space, and this is with the composite. What happens in the composite? Let me do all this thing. Okay, so basically, what imaging that you saw earlier. This is just focusing in air, and when you focus in the composite, you can see that there is an additional stretching, and that's what we saw in the earlier over here. This is in air, no composite. This is with composite. And the picture I'm showing it the next one. Okay. So mathematically, again, simple lens, Snell's law, you can do all these things over here and show how this D2, we said D1 plus D2 is T, but when you put a composite, this distance is changed. It's no longer, it's not, so obviously when you have multiple layers, that particular law will have to be changed. And this is the, yeah. No. Yes, right. Okay, so this is the what focusing point in composites. We saw that once you put a composite, it's sort of stretched in the down range.
Like, putting on this concept, these are about particle nature that we see in light, or the normal ray optics that we see. Is it related to particle?
See, ray optics, right in the first, it is like ray optics, but we have all seen how refraction takes place, right? But we are looking at refraction. We are changing the angle of refraction by using a material. I don't know what you will observe in. I mean, what is the advantage in the optical regime with a negative refractive index material? What would happen is exactly this.
Visible basically.
It will be this.
The optical regimes will be transferring the visible light to the other side.
Right. Yeah, but with optical images, the resolution become is good, and any lens will produce a nice will bring things to focus. We'll get an exact replica, right? Exact replica you can get, and the same thing we're getting in microwave, an exact replica at this point. Okay, so what we did was what we studied in the morning with time reversal imaging, but now the receiver signals are obtained with the lens in between in the path, and then so that's what we did. Okay, so these are the results. Then you have a metamaterial lens before you receive the signals. Pardon? No, I don't think this is a video. It basically shows, in this case, there is no lens. You have a receiver array, right? And the source, then you get the signal, you reverse it in time, back propagate, and it comes to focus at the source. In this particular case, there is no metamaterial lens. Down here, everything is the same, except that now we have used a metamaterial lens over here, and then receive the signal and propagate it. And you can see that the resolution of this is better than that. Okay. And the same thing, this is for source detection and then target detection. That means you not only you have the receiver array, and you also have a target. So this is the image that you would get, taking everything, back propagating it. You don't have much information at the target, but you have the source in the thing. And if you look at, you put a lens over here, okay, and then do exactly everything the same, and you will find that the target is imaged better than relative to this. So if I take a line scan across this, so when there is no lens, you get something like this, because the target is right in between over here, and in the red plot you get target imaging. I think something, let me see it here, cross range comparison, or is it? Oh, I'm sorry. The green one is with the lens, of course, and then the red one is without lens. Yeah, this is with no lens and this is with lens, right?
And the but that when a receiver is not able to receive that wave,
This is just a source detection, and we have not looked at the line scan comparison. But here, when you have a target over here, you can see that without lens, you get this red signal.
this the scale is representing the energy level,
Yeah,
the EM energy level.
yeah.
In case of first left-handed, this first image, in that case, the receiver array has a very less amount of energy that is receiving or getting to the receiver. That is not able to receive any information, and whereas in case of the second image, it has a good amount of energy that is being received there.
Yeah. See, there is the lens itself is lossy. So without lens, you definitely get more energy in the signal that's focused. But see, getting you can get more energy, but resolution is something different, right? How small can you detect, kind of thing. And there, with the lens, you see that it is better.
What was the scale represents what exactly? Y-axis means what exactly?
Over here?
Yeah.
Ah, okay. So it's just it's like y-axis and x-axis, both of them are in space. In space.
Graph as for the color coding.
Color coding is the actual energy image, energy density. Yes, back-propagated time-integrated energy. Energy in the time back-propagated signal, yeah. This one? On the left hand, this has, in what way? It depends on, cross range or down range. So in this range, in this direction, it is getting, both of them is, 10 to the minus 13, 10 to the minus 13, right? Yeah, it's in the source, it is just, the only thing I can say is, if I had two sources close by, this would give a better signal than this one. This is just imaging, and you can say that in this direction, in the downrange, this has a better resolution. Maybe they are comparable in the cross range. Okay, that's just true. Yeah, so we tried to reason out why is the image with the lens better, and the reason is, the reason why it's not better is because we have lost the high frequency information, and here we are keeping the high frequency information. So the final image has is more is get better resolution. So if let me go forward. So here you can see that indeed, if you look at just the line scan across, it's definitely better. So these are some additional examples. We just talked about if you have multiple defects, can I resolve that there are two defects? So what we did was, this is the composite, and we put two defects over here. The composite is epsilon r is 4, and there are two defects. This is the frequency we use. The lens thickness is 3 lambda 0. And here are then we did all these excitation, time reversal, back propagation, energy image, and this what we see here is just the line scan across. And without lens, on the defect location, this is what we see. And with the lens, we see kind of two indications. only the way you can design metamaterials to have a negative index at a specific frequency.
But you're talking about that high frequency material band pass filter. Such scenarios, how are we reconstructing back propagated?
Yeah, basically, when you do exactly what you said is amplifying in a certain band pass. So that information is there in your received signal. That's all. So when you back propagate, you get that signal is available to you. You are imaging with that. That's all. That's one way of looking at it. Everything's MATLAB. Yep.
So, that the lens, we didn't design that lens. For that vertical frequency lens which exists, like 12 gigahertz, 12.4 gigahertz, and then we make a slab of that lens, and then we all these simulate.
Right. So you have in the forward propagation, you have the lens. Well, the way we simulate is we don't, we're just looking at a slab with n equal to -1. That's all.
So these codes are for the finite difference time domain method, and quite Maxwell's equation.
Yep. Yeah, it's the same. Yeah, it's just the material property that's changing, right? The same equation, the same model. So once we generate the receiver array signal using a model, the time reverse, we are back propagating using the model, and those are the results I'm presenting. These are all simulation results. And here I have two defects, defect 1 and defect 2, as you see over here. And we see the spacing between the two defects is lambda 0/5. So obviously, when there's no lens, you have this dotted line over here. You don't really see the two. But then what we did was to move the source 1, 2, 3, 4, 5 different positions. And at each position, you can see the two bumps in the reconstructed image. So that is resolution. How can I discern two defects that are kept so close by? That's it.
What are these one?
Those are different positions of the source. So as you move the source, when the source is in 0.6, defect 2 has a higher peak than defect 1. When I put the source in at 3, then I'll have defect 1 has a higher amplitude. So by moving the source, you also know where the two defects are and that there are two defects and all that. So that's all the study we do.
Will it behave just like a normal optical lens that we use?
No.
I mean to say that our eye is going to behave, and the letters that we want to object, a defect. No, it's not necessary that it will always be on the surface. It can be buried inside that surface too. That we have to readjust that focal point. Is that the representation? That defects at different levels, for that the focus or the distance has to change, the focus point has to be changed. Because that the resolution is changed.
No. See, when you design, I don't understand your question, because when you designed your metamaterial lens, you know where it's coming to focus, right? In this particular case, okay, in this particular case, since we know where it is focusing, we can put the defect at the same point. But the defect can be anywhere in the sample. This is inside the sample composite, but at the location where it's coming to focus. When you saw, if you remember the ray diagram. So, and that is one of the reasons why you're getting such good resolution. Now, these defects need not be at that focal point. It can be at a different point. So we did a study on how much will the image deteriorate if it is away from that actual focal point. Okay. So it is very different from optical lenses. I don't think you have these kind of issues over there. Well, maybe not, because okay, in this particular case, you're saying that if your object is not at the focal point, it's going to be blurred. Oh, okay, now I understand what he's saying. Yeah, it's true, but ultimately we want to see whether we can discriminate. We can separate out the two defects which are lambda by 5 distance apart. This is an ideal case where those defects are at the focal point.
That case, the complement
Ah.
is that considering that to be a far field, all the wave patterns will be parallel plane wavefronts.
Yeah, in a way, yeah.
Then they'll focus on the same point.
Exactly. Yeah. No, but even then, see, even if it's a parallel wave, if you go back to, let me go to that picture. This picture over here. See, for a particular lens design, we know exactly what is D2 and where it should be. So if I put my sample and the defect inside the sample is at this point, then I get the ideal case. But I put the sample here, but the defect can be anywhere, right? In this, then there'll be some blurring. There will be some.
Same point.
Yeah, the focusing will always come to that point. It's possible that, you can bring the focus to what we could do, for example, is move this source back and forth.
Yeah.
So that this point will fall on the defect and then get a better, you will get, at some point you'll get, it's like, focusing in any camera. Yeah, you're right that there are complementary operations in the optical regime. Yeah. I wouldn't think so, because what is happening is, well, it's designed so that when you have this periodic structure, the overall, it behaves like a material with negative permeability and negative permittivity. And if it has those kind of negative mu and epsilon, this is how the light will behave. That propagation will have these properties.
Normally, when we have a lens this, so if parallel wavefronts are coming from there, that means every light is coming in parallel wave. So this lens is offering different, you can say phase difference actually, or path difference.
Yep.
That creates different phase for each wave, and they converge to a particular point.
That's correct.
Now, in case of metamaterials, it's not like the shape is not like this. The shape is like this itself, let's say.
Yep.
But it's made up of different FNR and mu r. So, and this you can say difference is such that the path difference being offered here is same like that of the optical lens, and they converge at same point.
Okay. Now, the second design does exactly what you're saying. In this design, the mu is not, the refractive index and mu and epsilon are negative throughout, and it's constant, doesn't vary, right? It's like a single, homogeneous block.
That is, and you said that corollary, the complementary is explanation is given this way. That they focus to a same point. Considering that same a particular frequency that is designed, and for that particular frequency, the focusing will be at a particular point.
Mm-hmm. Yeah, like you see over here. But I will, so that is the way, once we finish this work, this is exactly what we are thinking. So why do we make the periodic structures identical in 2 dimensions? Can we vary spatially so that the properties changes at each point? And then we can do exactly what the optical lens does. Okay, and I'll come to that after this. Okay, so yeah.
Let's say how much
It will, for frequency, I would say, because, well, the metamaterial has that behavior for a small frequency. Over that frequency is going to be, it will work to enhance.
Have done the analysis for focal point.
This is not fixed focal point. This is actually, we are moving the source parallelly and trying to see what happened. In this case, we have two defects which are spaced lambda by 5 apart. So it's a very, in the lambda space, it is small, close to each other. But we just looked at different locations in the same place. Yeah, so we have not really different focal point. It's the same. Once you have a metamaterial design, the focal point is fixed, right? But you can move the source away from the lens, like an optical source, and then the focal point will also vary, because there is a condition that D1 plus D2 is equal to T. The thickness is T, and this D1, and that's D2.
How we can know?
So here, I know the thickness of the lens. If I know D1, I know what D2 is, and that's where the focal point is going to be, because it has this D1 and D2 together has to be T. So that's why I can move this D2. That's what I showed in this simulation study. What was that? Yeah. So the simulation showed that when the source is over here, it comes to focus here. When you move it closer, then this moves farther. So simulation-wise, we showed, and that's also okay. And so we did the same thing. Yeah.
So the reference is that
The what? The FDTD?
yeah.
We just did it ourselves. I know a lot of people worked on it, but it's fairly straightforward, right? That's all. We just Saptarshi programmed it over a weekend. So yeah, okay. Where is this image? I don't have the right image over here. I'm just trying to see. This is the okay. So this whole thing is the energy image, time reversed energy image without lens. And this is the near field. And I don't have the image. I don't know. I did not. This is with lens. The red result is without lens. The green result is with lens. And you can see even D1 produces a peak, a small peak, D1, D2, D3, whereas the red shows only D2 and D3. Okay. So this is the same. I don't know why I don't have the image. I should probably, I forgot to bring that up. Oh, yeah. And I thought this must have been with the, this is without. Okay. Okay, the next one was experimental validation. Okay, simulation is always wonderful. You can always tune it to what you want. So we got this same the structure that was fabricated. These are the SRR structure. These are the wire structures. It was 20 by 10 by 31. So there were 31 of these plates, and 20 of this direction, 10 this direction. So there's 200 unit cells in each of these printed on this, and we put 31 of it stacked up, and then we have the transmit receive. And this is actually the frequency, looked at the frequency response of this. This is, I think, the simulated value. And yeah, this is the frequency. This is corresponding to left-handed peak. This is the S21 versus frequency. And this is what we call the left-handed peak where, and this is the n greater than 0 region. This small bandwidth is the n less than 0 region, okay, corresponding to simulation study. And we looked at in that region, okay, here is our negative index behavior. So we have the metamaterial lens here, and we basically looked at the transmitter. And if you look, and then we've scanned this region above. Oh, okay, let me see. So, so we scanned with the receiver, we scanned this whole region, okay, to look at the S21. And we can see that it appears that it is reflecting in the opposite or negative, it's showing a negative index behavior because it's the source is imaged to the left of the actual thing. You know, experimentally, it's not so, nothing looks so nice and clean. Okay. So we said, okay, that was good enough. This one? Yeah. 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 No, no.
The negative frequency is from the left side of this one.
Over here, I have S11 and S21, both are negative. I think from this, he assumed that this is the frequency range. And then looking at this magnitude, of course, it's you know, the experimental signal is so noisy, it's not so clear that we couldn't to make a conclusion. But using this in addition with what we have over here, we said, okay, this particular one must be the left-handed peak. You know, yeah, see this in this figure, both of them are negative at this point, certain frequency, and so we determined, okay, this must be the left-handed peak. And I think we did try imaging, and this is the only one that gave us the behavior that we expected it to have. And so that means we sort of concluded that the lens does behave like a negative index. Okay.
There's one more graph which should be there that it shows the refractive index behavior which is extracted from this S11 and S21, which exactly shows that it's having a negative refractive index. That means epsilon and mu both are negative.
Yeah.
Which is extracted from S1 and S21.
That's right. Yeah, S1, yeah. So that is not over here, you know. It's there in the thesis probably, but it was not there in this paper where we presented in this conference paper. Yeah, S1, from that you really have to determine epsilon, mu, and n. Then, okay, that would have shown, and in fact, I remember asking for that plot to be superimposed on that. So it was not done. So this is basically, oh, I've gone back. Okay. So then we went to application to NDE. I'm just going to get all this. So the lens, we got it fabricated in China. You know, to fabricate that in the US was several orders of magnitude more. We got it for $15 from China. And we, when we gave the design for manufacturing it in the US, was like $20,000 bill. So we just got, one of the students just brought it back with him and when he went to China. So thereafter, even all the successive fabrications, we just go there and get it done. Anyway, so let's see what do we have here. So application to NDE. So finally, we want, we have shown simulation results where we had 3 defects and all of them showing up. Can we do that in the experiment? It's not so straightforward. I don't think we really went to that particular level, but basically this is the schematic of our this experiment. This is the left-handed lens. There are 3 defects over here, and there's a transmitter, and then the receiving thing, we do scan this entire region above the lens. And okay, so this is what we do. What do we see here? So we have a monopole antenna on this side, and this is where we scan. The receiver probe is here, and we scan it all the way. Okay, this is for the Teflon sample. So basically, in this particular case, when we use the lens, when we put the lens here, we can see the 3 defects, in these 3 curves. When we take the lens out and do the same thing, we really don't see any systematic correlation between this signal and the defects that are there. So that was kind of a very crude, result saying, okay, with the lens, we even for NDE, it's possible. I mean, again, these are all very, very initial work. There's a lot of, we don't know how crude those, the lens itself is, right? Okay. So this was another GFRP sample. We have 1 defect here and 2 more over here. And at this frequency with the lens, we were able to see these, and at 7.4. And if you take a line scan, it does show 3 peaks. Again, it's we know what we want to see, and if you go there and we can look at it. So similarly, we did, we tried to do as much experimental result and see whether there is a promise. So I think there is promise in this approach, but a lot more work needs to be done. Yes, oh, that is absolutely. I mean, without that, then there's no point. Yeah. Once if you're using the lens, you've got to use the right frequencies. Right?
And here we have used a different lens for 7.2 and 7.4.
No, actually, we wanted to see. We didn't. We had the same, but these are some studies to show. See, if there is a small change in the frequency, but the negative bandwidth is also over the range of frequency. So both these fall in that same thing. And we want to see what is the difference, how does it change with the 2? Eddie, what was this thing? Okay, the simulation results, we also saw, we did all the time reversal imaging with reflected beams. So we wanted to look at, can we use the lens in a reflection mode? Because so that's what this is about, and you can see the results. So now the setup is quite complicated. This is the defect, the sample. This is the lens. The transmit and receive is on the same side now. Okay, transmitter and receiver. So this is our experimental setup. You have the sample on one end of the lens, transmitter and receiver. This is a monopole transmit receiver. They are all on the same side. And without a lens, we see nothing. Okay, and with the lens, we do see this the circular image, and this is a groove image. Again, there seems to be some correlation. I mean, it's fairly good. Okay, so we were talking with Prabhat about the next thing we did was to move from metamaterials to meta surface. This is similar to what Prabhat is doing with that sheet, right? So and this is the thing, you know, here we had the entire structure is identical. Okay, so the whole thing behaves like a homogeneous material with a certain property. So it is very bulky and it is lossy and somehow the quality deteriorates because of all those issues. So one thing we were looking at is, can I have a metamaterial lens or a surface where the property, where the unit cell parameters change spatially? So can that be used to exploit the negative index property? So yeah, so proceeding, okay. So we call this the graded index material lens or GRIN lens. It overcomes some of these limitations. And so this behaves just like this lens where your refractive index is going to change in that surface, so it can bring to focus over here. So that's that was the thinking. And so this is a unit cell. This also has been, I think, proposed by somebody else. So we took this unit cell, we varied this property, the gap between this capacitance plate. So this is the equivalent circuit for this. And so we simulated this and looked at the current density and the electric field distribution in this whole surface. And and the simulation showed that for different values of that gap, bit on the capacitance value, you're going to have different frequency behavior of the lens. This is the S21 phase, and this is the S21 magnitude. And for some, okay, let's see what else did we do here. So this is what we fabricated. So with the this is the profile of the refractive index that we see. And okay, let's see what's the result look like. So this is all done on HFSS. So this is the experimental setup. And the field distribution and everything with the lens looks like this. And I think without lens, it's just a diverging area. So this is all very, very initial results. And we did some experimental measurement of fields for this. This is with the lens and this is without the lens. Okay, those were all simulation. And then when we fabricated it, where is it? Yes, yes. Along each line, it's the same capacitance value. Only in one dimension. We can probably do it in 2 dimension too, which was not done. You know, we have to get it fabricated again and all that. So these were some, again, simulation results. This is with lens and without lens of what am I imaging over here? This is just in the focal plane, that's all. Source imaging.
How can we know frequency?
Oh, we can see we're not even looking at negative properties at all.
How will it prove we'll have the exponents to one, and from that data we'll calculate
Here we're just looking at how the phase refractive index changes. It doesn't have to be negative here. And we're just trying to focus it, that's all. So that it behaves like a lens to focus. Here I don't think we're looking at the this is not a negative index
He's trying
lens.
to get normal lens type of behavior, but
Yeah.
having graded.
Right, right. So it's slightly, you know, slightly different. And we were able to image. Let's see, where was that? I'm trying to look for the. Yeah, this is the with lens and without lens. Finally, okay. So this is the surface over here. This is the. There's a Teflon sample with the groove is over here, and the receiver is over here, the source, and the sample is placed at the focal plane. Imaging is done in, this is all done in transmission mode. So without the lens and with lens, we saw, this is very early results, and I don't remember all the details very clearly. I just picked it up this morning, before we left, because I didn't have this earlier, and I just went back and got these slides from his thesis. So basically, we did do a simulation, and the validation experimentally also, we do see a big difference between without lens and with lens. So it does come to focus nicely. And so we have to make sure we know where the focus is and put the sample right there. Works. But this is basically the idea. There's a lot of work that remains to be done. So this is just very, very early results. Started working on it, and then Srijan got a job offer. So he was in a rush to finish and leave. So a lot of it is written in the future work chapter of his thesis. And okay. No. But the source is right here. Lens means it's far field. Gigahertz.
Two books.
Over here, yeah. Yeah. I don't know, what's the wavelength that, what was the frequency that was used? Yeah. Well, the horn antenna, I think it would be become a plane wave before it reaches there. Has to. Otherwise, it won't be near far field. See, the horn antenna is kept at 150 millimeters, which is 4 lambda. Frequency is 8 gigahertz. Okay. So it is far field. And hopefully we'll have Srijan over here at NIT visiting you, giving a seminar on this topic. So more questions to address it to.
Lost tangent value. The metamaterial.
I don't have the exact number, but for the metamaterial lens, it was pretty lossy and dispersive. Yeah, okay. Yeah. But
require more power.
yes. That's why there was a lot of, I had a slide on a lot of disadvantages. I didn't put that thing, I just picked some of the slides over here, but it had a lot of disadvantages in terms of loss. It was bulky, it was lossy, and that's one of the reasons why we went with this thing. It's much, it can eliminate the loss quite a bit. And but again, we need to do a lot more work on this. We don't have all the answers. And I was hoping that Srijan will bring me another NIT student to work on that. So this is a possibility for any of you guys. And I think he has the full thesis, so you can take a look at that too. Right, you got it.
Sure.
Okay, so I want to stop over there for today. Any other questions here? No.
Can you throw some light on simulation part and actual development? How far we have reached? What are the current problems? Working on this? The making of mathematics.
That's what you saw over here. And I showed you a picture of this. This is a metamaterial surface, fabricated, right? And this is a negative index material lens. This is a negative index material lens fabricated. And most of the results I showed, experimental results, are using, we first characterize the frequency response of that, find out the frequency range over which it has negative index, and then excite it at that frequency. It's been, it's done. Initial work, this has, with a very crude lens fabrication. Maybe, I don't know how precise or how well good this is. But it can be done. Is that your question? Whether?
I thought one thing is
No. I started with simulation, and then that's why I had, if you look at this experimental setup, you have the lens over here, this whole experiment. I mean, the results look a lot cruder when you have experimental, because we didn't do it in an anechoic chamber. It was, there was so much of reflection, so much of noise. So it's a crude validation results.
Apparently, I know they have fabricated and they have displayed it in 3 terahertz range too, that it becomes visible.
Yeah.
They have
Yeah.
displayed it.
Right. It's an interesting area. Yeah.
And by using it for different purpose, by coating it on the airplanes, that it doesn't get detected for the radar.
Stealth aircraft, yeah. Yep. Yeah, so, in the beginning when you read, before we started working with that, it didn't look like it's possible, but it's possible. Those kind of thing. Okay. Any questions over there? Yeah. Yeah, you can actually, when we did time reversal imaging, we had the transmitter like this, the metal plate is over there, and the receiver array is over here. Yeah. Yeah. Yeah, you can draw a ray diagram and see what would happen, really. Because you have to apply Snell's law and see what happens if it's an angular incidence, how it would get reflected. We did try that, but why not? I mean, that's not going, the behavior will not be changed, but where it will come to focus is going to be different. Oh, meta surface you're talking about, okay.
That is actually of surface. That means by changing the angle, it will concentrate at some
Yeah.
point.
Yeah, so if you're This is the ideal thing, but if you know what happens in an optical case, you will have something very similar, even with the meta surface, because it behaves functionally. It's very similar to this. Yeah,
This is the case of the parallel wave front.
yeah,
What he is saying in that case, it will not be, though it will be parallel, but not parallel to the plane of the lens.
yeah. So it's good, but I know, but you can figure it out as well. I don't. We haven't done it. Okay. You tell me. You do it and tell me tomorrow. Homework. Okay.
Something today. But I don't know what the very much. But I know. The photo there.
You go. I'll take the picture. You go there. You also go and sit down.
Thank you.
I have other talents.
That's correct. Don't discuss them. Same schedule tomorrow.
Think so, yeah.
No, nothing like that. It's stored because we are limited, so it has to be formal. Nothing like a formal closing ceremony.
For what?
That is a formal closing ceremony to one.
I don't.
If there's anything, I will update you.
But closing ceremony should be after the inverse problem thing, because this is continuation.
Yeah.
And on the second part, though, we don't have, it's going to be on Zoom, so. Dr. Rao.
Thank you.
I think the topics are various. People can collaborate on, especially
We're already been
talking about.
starting out, so. A joint patient.
Fabrication, which you said from China, is it allowed in US that you can fabricate?
That's not official, I think.
No, in India, what they do is custom bricks of your product. First, if you import the product, it comes China, I think. They didn't.
They should detect.
The China is low cost for everything.
But this is. Don't know what it is.
So then in India, what happens is they will ask you what is the product that you have asked from China, all the. Some student brought it. Okay. I thought it was imported like to the.
Oh, no, that was only one sample which they got it as.
Student brought it in the bag, then you can obviously pick it. Then it's not.
What you are saying, but. have office and then
Why so many? It's happened in IT. We had ordered some fiber and some components. This we ordered, it was a $1,500. $50. China one was so complicated, the custom, then the clearance, then there's a Chopin notice.